All right, here's a second example in finding the rate law or the rate expression. And we're going to just take practice exercise number 2 from the textbook right here. If you want to copy all this stuff down, you're certainly welcome to do so. You can pause the video now. You can write down all the experimental data pieces. Otherwise, I'm just going to work it from right here. Pause the video now if you need to. All right, the following data were measured for the reaction of nitric oxide with hydrogen. Experiments 1, 2, 3, initial concentrations, initial concentrations, initial rate, initial rate, initial rate. Letter A, determine the rate law. Second, determine the rate constant and units, and then calculate the rate when NO is equal to and H2 is equal to. So for letter A, the first thing that we're going to do is compare two experiments where one reactant's concentration is held constant. So you can see from experiment 1 to 2, NO does nothing. It doesn't change. But hydrogen doubles. The initial rate right here, ignore the times 10 to the negative 3 part, goes from 1.23 to 2.46. Now if you can't see that that doubles, take your calculator out and take the big divided by the little, 2.46 divided by 1.23, and you'll see that it ends up being double, or E is equal to. And so if you want to do the math for this, remember what you do is you take the big divided by the little, so 0.2 divided by 0.1, take it to the x power, and that equals 2.46 divided by 1.23. And of course this ends up equaling 2, this ends up being equal to 2, and this is to the x, so that means x is equal to 1, so that means our hydrogen, H2, is going to be to the first power. So we found the first exponent, we found the first order for hydrogen. All right, now let's look at a second set of experimental data. Let's go from 1 to 3, because hydrogen remains constant. So now we can take hydrogen out of the equation, and we can look from 1 to 3 for NO, and you can see that it doubles. The rate goes from 1.23 to 4.29. So take the big divided by the little, if you're going to do the math part. Big divided by the little. So 0.2 divided by 0.1 from here and here. That's going to be raised to some power, let's call it y. And that's going to be equal to the rates, 4.92 divided by 1.23. Do that on your calculator and you're going to end up getting 4. 2.2 divided by 0.1 is 2 to the y power. Well, y's got to be 2, right? So y is equal to 2. That means that our NO has got to be to the second power. Okay? So now that we've got the orders, we can write the rate expression. And the rate law or rate expression is rate equals K, H2 to the first power, NO to the second power. Notice the only way we were able to experimentally to determine that is by using the experimental data. That's letter A. Now letter B says calculate the rate constant. So pick an experiment. I always pick experiment 1 because it's first, but it doesn't matter. And then put the data in, and the rate in. So the rate is equal to 1.23 times 10 to the negative third, and the units on that are molarity per second. That's equal to K. Hydrogen is 0.1. That's molarity, and it's to the first power. And then NO is equal to 0.1, and that's molarity, and that's to the second power right here. Okay? Now you're going to need your calculator here for a little bit, but 0.1 times 0.1 squared is 0.01. Take 0.01 times 0.1 right here, and that ends up, oh, don't forget to square the molarity right here. 0.01 times 0.1 is 0.001, and then that would be molarity to the third power, because it's molarity squared times molarity. You got your K right here that you're looking for yet. Don't forget that's a multiply sign, or let's just put it in parentheses because that's easier. And that is equal to our concentration, our initial rate right here. So rather than rewrite this here, let's divide both sides by 0.001 molarity cubed. So we'll divide this side also by 0.001 molarity cubed. Okay, these cancel, and now we'll have K. K ends up equaling, when you divide these right here, 10 to the negative 3's go away, 1.23. And the units, that's this answer right here. The units are molarity per second divided by molarity cubed. And remember, when you're dealing with this, put this over 1 and then multiply by the reciprocal. So it'd be molarity per second times 1 over molarity cubed. And then you can see that one of these goes away, that goes away, and so then our answer is 1.23 seconds to the negative 1, molarity to the negative 2, because we just got rid of one of them right there. All right, and then letter C, the very last one right here, is to calculate the rate when. Now that we know the entire rate expression and we know the rate constant, we can just plug this data into the rate equation. So rate is equal to 1.23, and then that's seconds negative 1, molarity negative 1, times our concentrations of hydrogen to the first power, so 0.150 molar, times nitrous oxide right here, 0.050 molar, and that would be to the second power right here, so that's second order. Multiply all of those animals together right here, and let's see, I don't think I did that on my calculator, so let's do that together on the calculator and make sure that I got that. Clear. 1.23 times 0.15, enter, that's that part right there. And then I need to multiply that by 0.05 squared and enter that, and I end up with a rate of 4.6. I get 2 sig figs on this, so 4.6 times 10 to the negative 4th, and the units on that would end up being molarity cubed right here, and we've got one molarity over here, so we end up with molarity per second, which is what rate should end up being. All right, best of luck on your rate determining problems.